Exploring the solar system, part 4, exoplanets. So the question is, why do we bother looking for planets around other stars? How do we go about finding planets around other stars? How might we decide whether or not a planet around another star could be harboring life? And again, the question, where next? So generally, it's interesting to look for planets around other stars, partly because they're there, but also you could say, well, are we going to get a better understanding of our own solar system if we look at how it works in other areas? Is our solar system typical, for instance? Do all solar systems look like ours? A few small rocky planets and an asteroid belt and then gas giants and ice giants. If they're not all like that, why are they not all like that? And does studying other solar systems help us understand our own? And we still have the question of, not only are we looking for exoplanets just because they might be interesting lumps of rock, but there's always possibility that there is life out there on some of these planets, and we would like to know the answer. So, how do we go about finding exoplanets? Again, with only half an hour, I'm not going to go into all of the detail, but there are nominally 5 different ways we can see exoplanets or find or discover exoplanets. One is the so-called radial velocity method. In other words, we're looking for wobble in a star. If a planet is going around a star, the star will wobble simply because if you've got a massive planet and a massive star, then the center of mass is some distance between them. And as the planet goes around the star will move slightly. So that's the so-called radial velocity or wobble method. Second method is transits, where the planet goes in front of the star and can cut out some of the starlight. So you're looking at the brightness of a star, looking for a dip. In neither of these cases do you actually see the planet. You're looking at the effect of the planet on either its host star or the amount of light from the host star. Third technique, you actually see the planet. Planets are very much fainter than their host stars, generally speaking, but if you can block out the light from the host star, then you stand a chance of actually seeing the faint planet. I'll explain that in just a moment. 2 other techniques, which I am not going to talk about because of sort of time constraints, and that is that we can also use so-called microlensing, the fact that if you have a star in front of a more distant object, the light from the distant object can be bent as it passes the star. If that star also has a planet, then the lensing of that star can be affected by the planet, and you can see a change in brightness of a distant object because of the light bending around the massive star and its somewhat less massive planet. But again, I'm not going to have more time on that. The final one is astrometry. Gaia, for instance, is a spacecraft that's able to map out the positions of stars. And if you watch a star long enough, you might be able to notice that it's corkscrewing through the night sky. And depending on how it is moving, you can deduce the existence of other planets based simply on its motion, as long as you can measure the position of the star accurately enough. And Gaia is basically the only space telescope we have that can measure stars to that precision. So I'm not going to talk about these 2, though they are mentioned in the handouts if anybody wants to grab one at the end. So method 1, radial velocity. We're talking about a planet going around a star, and depending on the mass of the planet, the more massive the planet, the more it makes the star wobble, because they're both moving around their common center of gravity. And so as the star moves towards us or away from us, the light from that star gets shifted. Doppler shift, the idea that the light is shifted towards the red if the star's moving away from us, or the light is shifted towards the blue if the star is moving towards us. Remember, we don't need to see the planet itself, we only need the light from the star. This is a slightly better way of representing it. I know there's a lot going on here, but if we imagine the top view is a planet going around the star, and the star is moving around the common center of gravity. As seen from the side, the planet goes from side to side, and the star moves to the left and right and comes towards and away from us. And the diagram in the top right shows the speed of the star And the spectrum at the bottom, compared to the cartoon on the previous diagram, it's not that the star looks redder or looks bluer as it's moving towards or away from us. What happens if you look at the spectrum from the star, you can see certain features, certain spectral lines, and it's these lines that shift a little bit towards the red or a little bit towards the blue. The color of the star doesn't necessarily change in any meaningful way, but as long as we have high resolution spectroscopy and can see the individual lines produced by the star, we can see whether they're moving backwards and forwards, which tells us the star is moving towards and away from us, and we can hence deduce the existence of a planet moving around. So this technique is sensitive to the mass of a planet going around the sun. Method number 2, looking at transits, is sensitive not to the mass of the planet, but to the size. As the planet moves in front of the star, if we're lucky enough to be aligned in the right direction, the amount of light from the star goes down. There's a dip in the amount of light coming from the star. Doesn't work if we're face on like that, but as long as we see it edge on, we'll see a dip. And the amount of light that's blocked depends on the size of the planet. It's not its mass, it's only the size that matters. If the area of the planet is 1% of the area of the star, then it will block 1% of the light, and we'll see the light drop to 99% of its original level. It actually works for different planets of different sizes. If we imagine hypothetically having a large planet going in front of a star or a small planet, the amount of light that's blocked by the large planet is a much deeper dip than on the right-hand side when a small planet blocks the star. All of this assumes that we know what the size of the star is in the first place, which is why we need to look at the spectrum of the star to work out what type of star is it and get an idea of what its radius might be. And from that, we can deduce the size of the planet that's blocking the light. It works for multiple planets. So if we have an entire solar system of multiple planets, each of them will be moving in front of the star at different times. So we might see the light output of the star drop, and then one planet moves away and it comes back again. Then another planet might move in front and we see a dip again. And then a second planet might start transiting at the same time. So we might get a rather complex variation of light with time. But as long as we've got enough data, we can start to figure out what solar system could possibly produce that change of light, what sizes and where must they be in order to give us this particular pattern. If we look at actual data, this is the cartoon of what we would expect, a light curve that looks a little bit like that. The blue dots are what we actually measure. If we take lots and lots of measurements of the brightness of the star, we get the blue curve, and then we try and figure out what must the actual shape be to actually give us that set of data. We try and fit the data to the smoothest curve that is consistent with a planet, a circular planet, moving in front of the star. If we look at actual data, this is data from the James Webb Space Telescope, unaffected by light coming through the Earth's atmosphere. The James Webb gives us really good data sets. So we look at the starlight intensity, and here it's nominally 100%. There's a little bit of noise depending on how bright this star is and how long we are exposing for to get our data. But then as soon as we get a transit, we see a clear dip in the amount of light, and we can work out how long it's taken to go from one point to the other, which gives us an idea of how fast that planet is moving across the disk of the star. If we know how big the star is, we can get an idea of the size of the planet. And by looking at how often we get these dips, do these reoccur every 10 days, every 100 days, every 1,000 days? That tells us the period of the planet going around the star. In this case, if you can't read it, the starlight has gone from 100% to a little less than 99%. So this planet is blocking out about 1% of the light from the star. If you've ever looked at the sun, you know that the edges of the sun are a little dimmer than the center of the sun, which is why this isn't just a square well, it's a curve, because the center of a star will be brighter than the edges of the star because of the way light is coming off the star. And so we can map out exactly what's going on if we have a whole set of data like this. The other technique is, because stars are really bright, if you can block out the light from the star, literally by putting a disk up. If I go back to the original, stars are far too bright to see what's going on. But if you block out the starlight, then you might be able to see there's actually a few faint points close, which are completely lost in the glare of the star. But if you can block the glare of the star using a disk, usually a small disk inside the telescope, and if you can position it correctly and make sure you're pointing in exactly the right direction, you can block the direct light from the star and hopefully see some faint points of light close by, telling you that you've got some planets. So here's a few actual examples. Here's a solar system seen face on. We've blocked the star in the middle, and you can see that we've got a few objects moving. Close to the star, they're moving faster than these blobs further away from the star, just like Mercury goes around the sun faster than Venus, which is faster than the Earth, which is faster than Mars. If I just play that again, if I can get this right, notice that this is data taken over quite a few years, so we can get an idea of how fast these objects are moving. And we know how far they are from their star just by measuring that distance. So we can get an idea of the mass of the star and deduce, if we know that we are getting any effects from method number 1, looking at the changes in the spectra, we can get an idea of the mass of the star and hence the mass of the individual planets. So here, this was imaged over, 12 years. It even works if you are edge on. You get a somewhat different perspective if you're edge on, but here the star is blacked out and then we see the planet when it comes out beyond the occulting disk, and we can see it going behind, and there it is again, goes backwards and forwards. So here we're seeing a system edge on. It's nicer, it's more aesthetically pleasing to see it face on as they go around the star, but it works essentially at any angle, which the transit method doesn't. With transits, you have to have the planet moving in front of the star in order to get a dip. But with direct imaging, as long as you can block the light from the star, you can effectively pick up relatively faint planets. In this particular case, this was again imaged over quite a few years, in this case 17 years or so. This idea of blocking out the central star, here the occulting disk is actually blocking out the star right at the center from this James Webb Space Telescope image of the star called Fomalhaut, Alpha of the Southern Fish. And here we've blocked the star and we're seeing not individual points of light indicating that we've got planets going around this star. We seem to have a dusty disk, and it's thought that, well, is this a solar system in the making? It hasn't yet apparently condensed into individual planets, but it does look like we've got a ring system, a ring structure. Are we looking at something which is akin to, is it similar to what you might argue would be an asteroid belt and perhaps a whole load of particles in a Kuiper belt? None of these seem to have developed into the individual planets that we know and love in our solar system. And the question again is this how all solar systems start? The more of these we study, studying one or two doesn't help. We have to study hundreds or thousands of solar systems, and then we get an idea of what is typical, and do they tend to start like this, or is this some different phase of a solar system, or is it simply that some stars do not develop planetary systems? It looks like planetary systems are very common, but it's also thought that some stars simply do not develop planets, and we're trying to understand exactly why that is. But if we think about the techniques we've been talking about, the idea of massive planets will make the star wobble and big planets will block light from the star if they happen to be in transit, if we're really lucky, we can find that we can apply multiple techniques to the same system. This is where the real power comes in. If we can actually use radial velocity, the wobble of the star from its spectra, as well as looking at the dip in the amount of light from the star, if we can use all of these techniques, radial velocity gives us the mass, because the star is moving around the common center of gravity of the star and the planet. Transits give us the size, and if we know the mass and we know the size for a given planet, then we've got an idea of its average density. And we know that if the density is really high, we're probably looking at a rocky world. If the density is really low, we're more likely to be looking at a gas giant. So if we have mass and size, we know density, and hence we know the type of planet we're dealing with. Spectroscopy tells us about what particular elements are present in the atmosphere, if there is an atmosphere of this particular planet. And we can judge the temperature if we know how far the planet is from its host star, because we can basically measure it. Then we can get an idea, if we know the temperature of the star and how far away the planet is, we can get an idea of the equilibrium temperature. And we can guess whether or not we're looking at an ice world, or whether we're looking at a lava world, or perhaps something in between. So if we have multiple bits of information, we can start to piece together what type of planets are we actually dealing with here. And we end up with the exoplanet zoo. This is not every exoplanet we know about. This is a tiny fraction of all the exoplanets we know. We are currently at many, many thousands of exoplanets. This here is possibly 1,000 or so. So it's only a few tens of % of all the exoplanets. They are labeled here to scale as best we can judge in terms of their size. They are to scale, and they are moving from left to right. They are cold and hot. In other words, the equilibrium temperature, if you were to place an object at these distances from their host stars, which are these types, what would you expect the surface temperature to be? Doesn't necessarily take into account the fact that they might have atmospheres which tend to keep them warm, especially if they have global warming, for instance, and the greenhouse effect. So this is really just at this distance from this star at that temperature, what would you expect the temperature of the planet to be? So really cold over on the left, rather warm over on the right. This particular graphic also has a few interlopers, because although it says exoplanet, some of these are our planets, just to give you an idea of scale. So we've got Jupiter, Saturn, Uranus, Neptune, and the rocky planets are dotted in there as well, just to give you an idea of scale. So just a reminder, we've got Jupiter and Saturn down here. So you can see some of these planets are bigger than our gas giants. Some of them are an awful lot smaller. But of course, if we are interested in, well, there's lots of planets out there, but we're really interested in the ones that are a little bit like the Earth, and in particular, where does a planet have to be to stand a chance of having liquid water? If it's too far to the left, any water will be ice. If it's too far to the right, any water will just be water vapor. So what sort of range should we be looking at for the Goldilocks area where we think water might exist as a liquid? Because we think that's a good way of starting the looking for life. Well, unfortunately, it's relatively narrow. These are too cold. And all of those are too hot. So the Goldilocks zone is not that wide. So perhaps it's no surprise that some, 90% of the planets out there don't appear to be particularly habitable in terms of not ideal for kickstarting life. And just again, to give a scale, Mars is actually there. It's a bit too far away from the sun. Venus is rather closer to the sun, is an awful lot hotter. And of course, we already know that Earth is in the Goldilocks zone because we know that we have ice and water vapor all coexisting on our lovely blue planet. So that just gives us an idea and a reminder. That doesn't mean we don't study all of these planets out to the left and out to the right, but we shouldn't be expecting to find any life on any of those. Doesn't rule out the possibility, but it doesn't seem very likely. Let's just have a look at some of these. I'm not going to go through all of them, as there's 1,000 of them, but some of them are quite interesting. One I thought was interesting is the fact that Proxima Centauri, only 4 light years from Earth, seems to have a planetary system. I assumed that it would be very difficult to find planetary systems out there. When I was a kid, the idea of finding planets around stars was absolutely science fiction. And then when it seemed like it was possible, I figured, well, there's not going to be that many of them. What are the chances that our immediate neighbor has also got a planetary system? It turns out it has. So our immediate neighbor, only 4 light years away, has a planetary system. Is that a fluke? Or does it mean planetary systems are pretty much everywhere? It now looks very likely that planetary systems are much more common than we first thought. maybe half of every star in the galaxy has got a planetary system. Remember, we're talking about hundreds of billions of stars in the Milky Way, so there are presumably hundreds of billions of exoplanets out there, something we didn't know a few decades ago. One of the oldest is this one, nicknamed Methuselah. It looks like this particular planet. We can't date a planet, but we can date the star it goes round because we understand stellar evolution, and we assume that planets are always born at the same time as stars. Can't actually prove that, but it's a reasonable assumption that when a star forms, it may or may not form planets. Planets don't spontaneously appear later. So this star is 12.7 billion years old, so presumably the planet that was found to be orbiting this star is also that sort of age. In the top right, we have one with a ridiculous surface temperature of 4,000 Kelvin. In other words, it's a planet very close to its host star. I can't remember if it's a particularly hot star or whether it's just literally very close, but the surface temperature might be thousands of Kelvin. And it's difficult to think of anything that could possibly exist in those sorts of conditions. The one in the extreme bottom right that looks like it's distorted is genuinely distorted because it has been calculated that this particular planet is so close to its host star, the tidal effects of the star will actually distort the shape of the planet. So we know our moon raises tides in the water of Earth, in the oceans of Earth. This planet is so close to its star, the star will raise tides on the planet and will effectively lock the planet into facing the star and produce a rather egg-shaped result. So that's not seen in terms of imaging, it's deduced from knowing its distance to the star and knowing something about the nature of the star. One of the largest, you can see again from scale, remember Jupiter is down here in the bottom left. This particular exoplanet, HATP67b, they've really got to sort out the names of these things. HATP67b appears to be enormous. It's something like 10 times the size of Jupiter or thereabouts, and yet it has a mass of much less than Jupiter. That means its density must be really low. Saturn has got a density close to water. This thing must have a much lower density than even water. It's been likened to the density of something like marshmallow, something like that. So very large, but very low mass, rather unusual. And again, trying to work out whether or not that there are lots of these or whether we've only just found a few of them. Just because we've only found a few doesn't mean there aren't more of them out there. And if we are going to start naming these planets, well, yes, they need to do a better job than HATP67b. I think the prize for the best name so far is definitely Coconuts 2b. Coconuts standing for Cool Companions on Ultra-Wide Orbits. I think they came up with coconuts and then thought, what can we actually make that fit, as it were, as an acronym? The idea is looking for planets that are orbiting a long way from their host star. Remember, we are 1 astronomical unit away from the sun, 1 AU, 150 million kilometers. This planet is 7,500 AU from its host star. At such a distance that instead of taking 1 year to go round its host star like we do, it might take maybe 1 million years to do one orbit. That is not the most bizarre thing in the entire zoo. I think the planet that's actually a very small one right in the middle there is actually one of the most weird ones, a so-called eyeball planet or eyeball ocean, because we know roughly speaking what it's made of. It seems to be small, relatively dense, the density a little bit higher than water. We think it's at the right sort of distance for water and ice to exist. But it's relatively close to its host star, and we think it's close enough to its host star to actually be tidally locked, just like our moon is tidally locked to the Earth, so the moon always faces one face towards us and never the far side. So it's thought that this planet is tidally locked to its star. So although it's made of ice with maybe water beneath the ice, it is thought that this is always facing the sun, its sun, and so it's probable that that ice will melt on the side that faces the sun, but stay as ice for the rest of the planet. So it is thought maybe it's an ice planet with an ocean where it faces the sun, and it always is the same side facing the sun. So it might well be a complete world of ice except for one patch, which is the subsolar point, the point facing the star, which is molten. So this is an artist's impression of an ocean surrounded by ice, and it gives this wonderful illusion of being an eyeball planet. So of course that's only an artist's impression, but it's based on the facts that we have determined so far from methods 1 or 2 or 3 of actually finding exoplanets. Some space missions have found exoplanets by accident. Gaia wasn't tasked with finding exoplanets. Gaia's mission was to map out stars in the Milky Way so we understand the dynamics of the Milky Way. But it did that with such phenomenal precision. The positions of stars were measured to something like 10 micro arc seconds. Phenomenal precision. The precision of Gaia's measurements are equivalent to measuring the width of a human hair at a distance of 1,000 kilometers. If you can imagine standing at John O'Groats and looking at somebody at Land's End and determining their position to the width of a human hair, that's the accuracy that Gaia produced. And so it's able, after many years, to look at the positions of stars, and some of them were wobbling in a way which was not consistent with simply the parallax from the Earth's motion or the motion of the star through the Milky Way. It was determined that they must have exoplanets going around them. So Gaia found exoplanets by accident. James Webb is able to basically block out the light from stars and see if there's any exoplanets there. That's not its main mission, but it is able to do that. There are plenty of missions that are explicitly trying to find exoplanets. Kepler found thousands of them when it was operational back in the noughties and the teenies, and there are others there. I won't talk about all the details, but you can go and search web pages to find out more about these various missions. Something I'll just note about Roman, the Nancy Grace Roman Space Telescope, hopefully to be launched next year. It looks like it's escaped the axe of a certain president who doesn't like certain space missions going ahead. It looks like the Nancy Grace Roman Space Telescope will fly next year, as well as the idea of we can find planets around other stars by putting an occulting disk inside the telescope, a tiny one, not one that large, a tiny one inside the telescope to block the light from the star. It's often said that if you want the best contrast of a distant object, you don't want the light from the star even to enter the telescope. Rather than let it into the telescope and then try and block it, you'll still get scattered light inside the telescope. So one thought is, can we block the light before it gets to the telescope? And they are not necessarily going to go ahead with this, but it's an intriguing idea that you send up Nancy Grace Roman with a huge star shade, which you unpack and unfurl. Wonderful piece of origami. This is about 100 meters in diameter. You then fly it a long distance away from your telescope, and you try and make sure you've got the choreography right, such that the star shade is flown 50,000 kilometers away and then blocks a distant star. And when it blocks the distant star, you will then be able to see the planets going around that star. So if you've got a candidate solar system, maybe this is the way to do it. None of the starlight actually enters the telescope because it's shaded thousands of miles away, and so you only get the light from the planets coming into the telescope. You should be able to see much fainter planets this way, but you end up with this choreography problem of making sure you can station keep a huge star shade to make sure that it's perfectly lined up with your telescope. So technical challenges, but not insurmountable technical challenges. Let me finish with the idea of, if there are exoplanets out there, how might we go about looking for life on these exoplanets? Well, remember, with transits, an object, a planet, might go in front of the star and might go behind the star, if we're lucky enough to be lined up with its orbit. That means if we look at the total light coming from the star and the planet, again, we don't need to see the planet, but if we look at the light coming from the star and the planet. When the planet goes behind the star, we lose the planet's light. So if we look at the spectrum as the planet disappears, the spectrum should change if we're getting light from the planet. And whatever that difference is, that must be light from the planet. And if we look at which molecules are present from the spectrum, we get an idea of which molecules are in the atmosphere. The same is true when the planet is in front of the star. Some of that starlight will now be passing through the atmosphere of the planet. If the planet does have an atmosphere, some of that starlight will be traveling through the atmosphere of the planet and might be absorbed by some of the molecules in the atmosphere. So although we draw the cartoon as we get a dip when a planet moves in front of a star, depending on which wavelength we use, we might find some wavelengths are absorbed by the atmosphere and some aren't, depending on which molecules are present in the atmosphere. And that is precisely what has been done, for instance, by the James Webb Space Telescope. Here is the starlight dipping as a planet goes in front of the star. But if we do that at different wavelengths, so the dots here are colored differently depending on the wavelength, and you notice that if we take a set of dots there corresponding to one wavelength, we get a certain amount of dip. It's blown up at the bottom here. But we get a slightly different level if we look at a different wavelength, implying that something in the atmosphere is absorbing one wavelength more than another. If we do that at lots and lots and lots of different wavelengths, we can effectively map out what is the spectrum of that planet. And we know that certain molecules absorb certain wavelengths, so we can start to identify this planet appears to have water and carbon monoxide and carbon dioxide and sulfur dioxide. We can identify particular molecules in the atmosphere of a planet simply by looking at its spectra. I say simply, it's a technical challenge. You need a nice spectrometer on a really big mirror like the James Webb Space Telescope to get reasonable data. But it is possible to work out the chemical composition of an atmosphere of a planet going around a star 1,000 light years away. The fact that you can do that at all, let alone start to deduce what the hell is it made of, what particular molecules are present, the fact you can do that, again, that would have been science fiction not that many decades ago. The fact that you can see planets around other stars and you can figure out what's in their atmospheres. We haven't yet found the signatures of that atmosphere of that planet is an indication that life must exist on that planet. But if James Webb keeps doing studies like this, if it keeps looking at different exoplanets around different systems, we hope sooner or later it's going to start picking up signatures that would only be indicative of life rather than naturally occurring molecules. Let me finish by just giving an idea, a graphical summary of what we've been talking about. This is a map of all the exoplanets plotted with their mass on the vertical scale, massive at the top, less massive at the bottom, and how long they take to go around their host star. Here's our planets, just to give you a point of reference: Venus, Earth, the gas giants and the ice giants. And if I run the animation, as time goes by through the 1990s, we started to pick up different exoplanets. As we go into the 2000s, the Kepler space mission started to pick up much more in the purple, which is the transit method. It started to find hundreds and it started to find thousands of exoplanets. So you can see we're now building up a picture of the characteristics of these exoplanets. This particular graphic goes up to 2024, and of course we've been building it up over the last year as well. You might say, well, does this mean that all the exoplanets that are out there don't look like our solar system because they all appear to be more massive than the Earth, and they all appear to be closer to the Sun with shorter orbital periods than Jupiter, for instance? But we have to remember observational bias. It's easier to see more massive planets because they make the stars wobble more. It's easier to see those that are close to their Sun because, again, we can see that wobble, and it's a period that's short enough that we can see this planet and the planet comes around again and the planet comes around again. If the orbital period is thousands and thousands and thousands of days, then we're not expecting that planet to come around very often. So it's much more difficult to find those planets. So the ones in the top left are easy to find. The ones in the bottom right are tricky to find. So just because we haven't got lots that are dotted around the Earth doesn't mean they're not there. We have to do a very careful statistical analysis to say, if we're not likely to see them, then what can we learn from having found this many Jupiters and this many Neptunes and this many rocky planets similar to the Earth? We think it is very likely that Earth-like planets are out there. They're just much more difficult to see than other planets, which is why we've got missions coming along in the future, not only in the near future, like Plato and Roman. Roman is a NASA space telescope. Plato is a European Space Agency telescope. But there are other plans into way beyond 2030 of having other telescopes which are explicitly looking for signs of life around other exoplanet systems. If you want to know more, all the information about every exoplanet that's been found is documented in the NASA dashboard up there. If you take a handout, you don't need to make a note of those web pages. They're in the handout. If you want to go and learn more about Coconuts 2b or any of these other exoplanets I've been telling you about, you can explore there or go find more about future missions that are coming up. Thank you very much.